Okay, so welcome everyone. Today we are really happy to have Joris Josiek coming from Heidelberg, who is going to talk about fundamentals of radiative transfer in expanding media. So just a little bit of information about our speaker. So he's currently a PhD student in Heidelberg, and he is working on combined evolution and atmosphere modeling of very massive stars. And this is extremely timely because it just has put on the archive 1 or 2 days ago a paper that it just get accepted. So if you are interested, please check out his paper. So it's exploring the connection between atmosphere models and evolution models of very massive stars. So that could be of interest for you. So as I said, he is a PhD student and he expects to be graduating to 26 or 27. And he did his master's studies in University of Geneva just before. Okay, so Joris, are you feeling ready?
Yeah, everything's good. I hope there's no more technical issues, but if there are, I apologize.
No worries. Then the floor is yours. Please go ahead.
Okay, well, thank you very much. Thank you for this nice introduction, and thanks also for giving me the opportunity to give this lecture. So, as you heard, I'm mainly working on evolution and atmospheres. This lecture series, of course, is about stellar winds. And as the first lecture in the lecture series about stellar winds, this is going to be a very fundamental background lecture. So a key component of a stellar wind, of course, is radiation. And this lecture will then explore how radiation can be transported through a stellar atmosphere through means of radiative transfer. So let's see if I can move this slide forward. Yes. Okay, so let's start with a quick motivation. So as we all know, radiation in hot stars specifically interacts with matter in very complex ways. And what we want to do as scientists studying these stars is have some background theory and models to explain how observations of stellar spectra arise. And this includes basically understanding how radiation interacts with the matter in two ways. One of those is trying to explain emergent spectra, such as this one. This is from a model that you can see here. And on the other hand, also how radiation can transfer momentum onto the stellar wind. So in all, this is a fundamental part of the analysis of stellar atmospheres, which is what we do. So here in the spectra, you just see an example of a typical wind line from a fast wind. So this is what most of you probably know as a P Cygni profile with a red emission component, blue absorption component. And computing or predicting why these lines happen is exactly at the heart of radiative transfer in hot stars. So most of you have probably had some sort of introduction lecture to radiative transfer. So here I'm just going to repeat the basics so that we're all on the same page in terms of definitions and key equations. So the quantity that we're talking about here the whole time is the so-called specific intensity. So the specific intensity is basically the energy transported by radiation per area, per solid angle, per time, and per frequency. And in general, this is a function that can depend on all of these quantities, so frequency, location, also direction, and time. And the key difference is between specific intensity and maybe the more intuitive concept of the flux is that unlike flux, the specific intensity does not actually dilute over distance. So the only way it's affected is by interaction with matter. And this is governed by the very famous radiative transfer equation, which you see here. So this is the radiative transfer equation in its most general form. By the way, in equations in this talk, I will always try to explain the most important parts, but don't feel the need to try and understand every single detail. I'll point out what's important. So here, what this means basically is what we have the change both in time and space of the intensity is caused by some emission minus absorption. So this is the intuition. It's quite clear. The absorption is proportional to the intensity itself, which makes this a differential equation. And this proportionality factor is the so-called opacity chi. And this will pop up in many places in this talk and also beyond. And this general equation has analytical solutions, but these are usually only for very special cases and not really for real life applications. So it's usually integrated numerically, which is very expensive. And depending on method, it has different levels of accuracy. So what we want to do is solve this equation, but we want to do it in some clever way that is fast but still accurate. So for this now, I need to introduce some geometrical concepts to you. So of course, we're looking at stars mainly, or objects that have some sort of spherical symmetry. And because of the spherical symmetry, we can use two different kinds of geometry. So let's see on the left here is this this diagram basically shows you the geometry of our system. So we have our star in the center, and we can use two different kinds of coordinate systems. So one of those is called so-called PZ geometry, which is a Cartesian coordinate system where Z points to the right, or in general in the direction of the observer. So the observer is located on the right of this diagram. And then P is this transversal coordinate, also called the impact parameter. And you can parameterize every point in the stellar atmosphere by a PZ coordinate. At the same time, you can also transform this into so-called polar coordinates, which is this R theta geometry, which basically gives you the same point, but is a function of distance from the center and this angular offset. And to make things a little bit easier later on, we usually define this parameter differently. So instead of the angle theta, we usually refer to mu, which is the cosine of this angle. And one more thing is that, of course, we are looking at three-dimensional systems, but in this case, this reduces to 2 dimensions because of the spherical symmetry, that we basically say that everything is independent of azimuth. So everything only has 2 coordinates. And then this means you can rewrite this radiative transfer equation, ignoring the time component, in 2 different ways. So here you can write it either as a function of R and mu, or as a function of P and Z. And what this means basically is that you're looking at a ray of light propagating into the direction of the observer. So in Z direction, this is like these arrows that you see here. And this basically describes how the intensity changes along this path. Before we move on, there's a few definitions which are probably familiar to a lot of you, which we need. One of those is the optical depth. The optical depth is a dimensionless quantity, and it's basically the integral of over the opacity over the photon path. And this is usually defined from outside to inside, so viewed from the observer, going deeper into the star. And then we have the so-called source function. The source function is just this emissivity divided by the opacity, okay? And this, like the emissivity, it describes how the atom emits radiation or scatters radiation. And it's also a very central quantity. And this source function is usually a function of the population numbers of the atoms. Okay. Then another central quantity that we'll be using a lot in this talk is the so-called profile function. So what you do in here is that you say you have the opacity of a line, and this opacity depends on both frequency and position. So each position and each frequency, there will be a certain absorption coefficient. And the profile function is used as a way to separate this into 2 functions. So you have this opacity, line opacity component, which is basically the integral of the opacity over the frequency. And this basically then only depends on position. And the variation over frequency is only captured inside this profile function. And this profile function, therefore, is normalized to 1. And it looks a little bit like this. So it has a certain width. And this width is just the natural broadening of a line. It's due to thermal motion, so just random motion of the particles within the line of sight means that each individual particle is right-shifted or blue-shifted slightly, so you don't have a thin delta peak as a line, but some sort of width. And what contributes to this, as well as the thermal motion, can also be random motion, such as turbulence. And then the width of the line is basically just proportional to the thermal velocity of the particles. So coming back to the motivation of this talk, is on the right, we have this emergent line profile, is what we observe. And then on the left, we have the intrinsic line profile, which is just this very thin peak, or very narrow peak. And you can see here there's a difference, because the intrinsic line profile is narrow in the sense that it's proportional to the thermal velocity, which is on the order of tens of kilometers per second. Whereas the width of this emergent line profile is on the order of the wind speed, which can be thousands of kilometers per second. So the entire question of radiative transfer in this problem is saying, how do we get from one to the other? And how we get from one to the other is by solving the so-called formal integral. So the formal integral is basically the most general solution to the radiative transfer equation, and it gives you the intensity as a function of optical depth at each different frequency. And it takes into account some boundary conditions, so intensity at a reference optical depth, tau 0, and you also need to know the source function. So, okay, we could say done now. Thanks for coming to my talk, but of course this is a little bit more complicated. So there are problems with integrating this numerically. So one, of course, is still, where does the source function come from? I'll mention this later, but for now it's still a mystery. And in general, this requires very highly resolved grids in both space and frequency, because of this problem that we have very narrow lines, intrinsically narrow lines, but very fast winds. So you need to resolve frequency in very, very small steps in order to really sample the entire line profile everywhere in the star. The other problem with this, in the context of an expanding medium, is that opacities and emissivities are not isotropic because of the Doppler-shift. So because depending on which direction you look at a specific atom or a specific gas parcel from, it will have a different relative velocity to you. So the line will be Doppler-shifted into different frequency space, depending on which direction you look at it. So opacities and emissivities are therefore direction dependent. And they also depend on the location, of course, in the star itself. So because of all of this, we have still a big resolution problem. And this causes large errors. So if the resolution is not sufficient, integrating this naively like this will not result in accurate results. And therefore, we still have a computation issue. So this brings me to the so-called Sobolev theory. So this is a theory originally developed by Sobolev in the Second World War. Excuse me. But formally written down and published in the 60s. This Rybicki and Homer paper also solves this in an elegant way. So if you're interested in a more deep dive into this theory, this is also one to recommend. So this theory is a way to somehow simplify this problem. So our problem is still, we want to figure out what the intensity of radiation is at any point in the star. So for this, I introduced to you the concept of the resonance zone. So on the left is an animation. I hope everyone can see the animation moving. I don't know how it is with the connection, but so
works. It works.
It works. Okay, thank you. So I'll walk you through this. And I'll spend some time on this slide because it's a very central concept. So if you haven't heard of the resonance zone before, this is now the time to pay attention. So let me first talk about this plot on the left. So what you see here is a star. The star is in the center of the slide, of the plot, in black. The observer is on the right. So I've introduced this geometry before. The observer is on the right, So to the left of the star is a shadow, so you can't see behind the star is what this means. And then around it is some stellar wind. And the stellar wind is emitted radially from the star, which means that at every point outside of this core, you have the gas has a certain projected radial velocity in your direction or away from you. And this is what this color means. So all of this part on the right of the center is basically blue shifted. It's moving towards you, and everything on the left is red shifted. And now what you see at the bottom is what's moving is some photon frequency. So what we're considering here is some spectral line, and one individual spectral line with a rest frame frequency of μ0. So this is μ0. And then you have some photon that has a different frequency nu. And as this photon is traveling through this atmosphere, it can basically only be absorbed if it's near this rest frame frequency of the spectral line in the comoving frame. So what you want is you want the spectral line to be Doppler shifted into the frequency of the photon. And this is the concept of this resonance zone. So the resonance zone is the zone where the gas is moving at exactly the right speed for the central line frequency to match the photon frequency of the photon we're considering. Not exactly, but within the width of the intrinsic line profile, so within a few thermal line widths. So this is what this equation basically tells you. And here the animation shows you where this resonance zone is with a variable photon. So if the photon is slightly bluer than the line center, and so these are in units of V infinity of the terminal wind speed. But if the photon is slightly bluer, the resonance zone will be on the right. It's basically the part of the star that is moving slightly towards you. This is where the blue photon, slightly bluer photon, can be absorbed, interact with the medium. And if it's red, so if the photon is slightly redder than the line, it will be on the left. So you can see how the resonance zone moves depending on the photon frequency. Okay, so this is the same plot, but in a slightly different perspective now. And now we fixed the photon frequency at a certain frequency relative to the line center. So again, only looking at one specific spectral line, any one. And we have a photon now that we consider, which is slightly bluer, so slightly higher wavelength, higher frequency than the spectral line, and also with a thinner, narrower line profile than in the previous slide. So we have the line profile here on the top right plot. And you can see as the photon moves through the star towards the observer, it does not interact with the medium at all because it's too blue. So it's not in the same frequency space as the Doppler shifted spectral line. Again, we're not considering multiple lines, only one line. So if the line is not at the same frequency as the photon, there is no interaction. And then as it moves through the medium, at some point it will reach this resonance zone. So it will basically synchronize with the motion of the medium, where the medium is moving at exactly the right speed that the spectral line is also blue shifted into the frequency of the photon. And this is where then the photon can interact with the medium. So what this means is that if you look at the evolution of the intensity with the moving photon, is it will have some sort of constant intensity, I0. And then it will move through the medium and stay constant. And at some point in just the resonance zone, it will drop. So the photon will be, well, the photon package will experience absorption, and then the intensity will drop. And it will drop exactly by this exponential of the negative of the optical depth of this resonance zone. And the optical depth of the resonance zone is also known as the Sobolev optical depth. So why do we do this? What is the advantage? Well, the advantage is in the case where the resonance zone is narrow. So narrow means macro variables are constant. So opacity, source function, velocity gradient are constant in the resonance zone. And this is the case, of course, of the thermal velocity. So the intrinsic line width is much smaller than the wind speed. In this case, we have the advantage that we can ignore most of the medium. So instead of performing some sort of integration of the radiative transfer equation, you actually only need to look at the interaction in the specific resonance zone, which we can later reduce to one single point in this approximation. So this is the core of the Sobolev approximation, explained graphically. But now we want to do some math to solidify this a little bit and develop it further. So the question here, mathematically, what we need to calculate is what is exactly this optical depth, this Sobolev optical depth of the resonance zone. How do we obtain this? By the way, here, if any of you, for teaching reasons, are interested in the code for this animation or the one on the previous slide, feel free to contact me and I can send you the Jupyter notebook. Okay, so what is the Sobolev optical depth? So now there will be some equations, but hopefully I can walk you through them one by one in simple terms. So as I introduced before, the Sobolev optical depth is an integral, or any optical depth is an integral over the opacity. And we've seen how the opacity can be split into a purely space position dependent component, which is just the total line opacity, and this comes from atomic data, multiplied by the so-called profile function. And the profile function is a function of the frequency, but it is always a function of the frequency that the atom itself sees. So this is not the observed frequency, but this is the local co-moving frequency of the photon shifted into the frame of reference of the moving gas. So the so-called co-moving frequency. And then you integrate this, as always, over the photon path. And the co-moving frequency, you can see this relatively simply, is just the frequency of the photon, which is nu, multiplied by some local Doppler-shift. So this shifts the photon frequency into the co-moving frame, and it's dependent on this projected velocity. So it's the velocity of the gas. So this is just the wind velocity v, multiplied by this geometrical factor, this cosine of theta. And then this you can insert here. And then what you want to do, though, is integrate over dz. So here we have the first time seeing how we have to use two different kinds of geometry in the same equation. So this is why it's important to always keep in mind you have this Cartesian geometry of pz and also the radial geometry of r and mu. And what you do here is you change the integration variable. So instead of integrating over dz, we integrate directly over this co-moving frequency. And this transformation happens by, like you do any transformation or substitution in an integral, you need to calculate the derivative of the new variable with respect to the old variable. And this you can do with the equation on the top right. But since it's in polar coordinates and you're doing it in pz coordinates, there are extra terms that you have to take into account because of this geometrical coordinate transformation. And if you do this, so here are mu expressed in pz geometry. If you do this, you end up with this expression here. And what you do with this expression is you put it back into the integral, and then you end up with something that looks like this. So we can just look at this first part here. So the Sobolev optical depth. So again, the optical depth of this resonance zone is just integral over this giant number here, and then the profile function of the co-moving frequency integrated over the co-moving frequency. And now comes the heart of the Sobolev approximation in mathematical terms, is saying that the resonance zone is so small, or small enough, that macro variables, or all sorts of variables that play a role here, are constant. So this means that this giant term in the front of this expression can be pulled out of the integral. So what you need to do is only calculate this within the resonance zone. So you first need to find the position of the resonance zone, and then you can calculate what this term is. And then all you have left is an integral over the profile function. but this integral is relatively simple. So in total, the integral is just 1, so because of the normalization. And then if you don't integrate totally and you want to have the optical depth at each point, then it's some sort of error function, which looks like this at the top. So you integrate with the photon path, which means you integrate from blue to red. And then first, before the absorption, the optical depth is 0. And then as you integrate, at some point you reach the resonance zone, and then you go through the resonance zone, and then the optical depth will jump to its maximum value. So this means that the total Sobolev optical depth is just, neglecting this integral, this factor in the front, which you can very easily calculate. What have we actually achieved here? Well, we've already removed one integration from this problem. So we no longer need to integrate to find the optical depth. At each point, we can calculate it from a closed expression. And of course, this still has to be done for each different photon frequency and each different impact parameter, because depending on what the impact parameter is relative to the center of the star, the resonance zone, the Z coordinate of the resonance zone will be in a different place. So this is what you saw graphically on a few slides ago. Okay, so now we have this Sobolev optical depth. And now from this, it's quite easy to get to the intensity, because we have the closed formal solution. So to find the formal solution in the Sobolev approximation, you do two things. For each frequency and impact parameter, you find the location of the resonance zone, and then you compute the Sobolev optical depth according to the last slide, and then you can calculate the intensity at each point. So in the intensity before passing the resonance zone is unaffected by any sort of absorption. So it's just the back intensity, the illumination from the back. And then after passing the resonance zone, it's the same intensity coming from the back, but modulated by the exponential of the optical depth of this resonance zone, plus the source function in the resonance zone and in this term here. And in general, you can see both are combined in this general equation where you include this so-called integrated line profile, which is basically 0 before passing the resonance zone and 1 after passing the resonance zone. And then it's relatively easy to see how you can reproduce both equations. Okay, so what does this mean? Well, for the intensity also, we now have a closed expression that does not require an integration anymore. So this brings me to my next point. So this is now we can talk about a new concept. This concept is the concept of the profile weighted mean intensity. So what what the idea is here, okay, now we can calculate the intensity in any place, but we still require knowing where the resonance zone is for each nu and for each p. But now if we want to do physics with this inside the star, so what we want to do is calculate the rate equations. So we want to know how the radiation or the absorption of radiation will impact statistical equilibrium of electrons inside atoms. And also we want to compute radiative acceleration. So again, how absorbing the radiation can transfer momentum onto the atom. So what this means is that at a certain position, we don't actually, for this purpose, we don't need to know the intensity across the entire spectrum. We only need to know the intensity in the place where the photon can be absorbed, so around the local line center frequency. So this is the mathematical formulation of this is this I bar. It's the profile weighted mean intensity. It's the intensity weighted by the local line profile. So along a certain frequency or at a certain point in the star, in order to calculate interaction with matter, we only want to know the intensity over this line profile. So what this means is basically mathematically in this term, it means that this nu of the intensity has to be close to the center line frequency in the comoving frame. So only components, basically only components where the profile function is strongly non-zero will contribute. So this is what this means. Only photons with a comoving frequency close to the line center contribute. And what we do then, okay, and by the way, I'm trying to explain this now in a few minutes, but this idea is not necessarily trivial. So you should not feel bad if you don't get your head around it immediately. It takes a while, but if you're interested, I really recommend looking it up and looking into it, because what happens now is very elegant. So what you do is, in order to perform this integration with this intensity equation from the previous slide, you can change coordinate systems. So from PZ, we go to our new geometry, and you integrate directly over the d of the profile function, of the integrated profile function, because it's already here inside the expression. And what happens when you do this is you get an expression that looks like this. So what have we achieved here? Well, this is still completely local, so it requires no integration for calculating it. But importantly, also, it does no longer require knowing where the resonance zone is. Because if we look at a specific point in the star, and you want to know what photons are being absorbed at that point, you don't care about photons who already interacted in other places in the star, so whose resonance zone is far away. You don't care about that. So you only care about photons whose resonance zone is close to the point that you're considering. And because of this, there's no longer the concept of a separate resonance zone. It just all goes into this location parameterization here of R mu. So this is super nice. We have a profile weighted mean intensity dependent only on position. Okay, now you can relatively quickly perform an expansion. So some limiting cases, if the Sobolev optical depth tau s is very, very small or very, very large, and you obtain this these approximations, these limits. What I should also say, by the way, is that this I back is the back illumination of the gas, and this depends on where you are in the star. So if you're in a place where that's in front of the core, then this back illumination is whatever intensity is coming out from the star itself. And this is generally frequency dependent. Otherwise, if you're outside, look off center by more than a stellar radius, the back intensity is either 0 because you're looking through the entire atmosphere, so on the back is just empty space, or, and this is where things can get complicated a little bit, is if you are in a binary system and the back illumination can actually come from another object, like a companion. So this is what this I back means. It has a different values depending on where one considers the position. We can go on from this. So I mentioned that knowing this profile weighted mean intensity is useful for computing the interaction of radiation with the matter, which is essentially what we try to do in these stellar atmosphere codes. And then we use this to compute two different parameters, two different quantities, J bar and H bar. So this J bar is the mean intensity, and this is what you use to then compute rate equations. So this is couples to the equations of statistical equilibrium and will then tell you how the electrons are distributed inside atoms. Whereas this H bar is used to compute the radiative acceleration. And another interesting bit, or very useful bit of mathematics here, is that if you want to compute H bar, you actually don't need to know the source function, because of the geometry and the fact that only mu squared plays a role in all of this, in the different terms that I showed you earlier. This means that this I bar is actually what is called 4-aft symmetrical. At least the second term of I bar is. So this term here that is dependent on the source function. And if you multiply this with another mu, it becomes anti-symmetrical in mu, which means that if you integrate, this last term does not contribute. It becomes 0. So this is quite useful. This means that you don't need to know the source function in order to compute the radiative acceleration in the Sobolev approximation. So this brings me to my next part. When can we actually use the Sobolev approximation? So it's all nice what we've done. It's very fast. So we don't need to integrate to obtain the opacity, and we don't need to integrate the opacity to obtain the intensity. Everything is just one expression. And so I want to remind you of the fact that the assumption that we made here is that the resonance zone is small. And what that meant is that we can pull out all of these macroscopic quantities out of the integral so that they're constant, basically. And mathematically, the condition for this is that the scale height of some variable, so the length where some variable changes significantly, must be much larger than the width of this resonance zone, also known as the Sobolev length. And this is on the order of the thermal velocity, because this width has to do with the intrinsic line profile width. So we saw the wider the line profile, the bigger the resonance zone. It's quite clear. So this means that we can use it in places where there's a fast wind. So anywhere where the thermal velocity is much, much smaller than the wind velocity is a place where we can apply the Sobolev approximation. So winds above the thermal point, and also supernova remnants. And the special case of supernova remnants is that their winds have a constant velocity gradient. So dV/dr is a constant always. So this also implies that we can use the Sobolev approximation. So these are the two main cases. Where it is not appropriate is for any lines, spectral lines formed below the sonic point. Because we can easily imagine why this is, because there the wind velocity is smaller than on the order of the thermal velocity. So what this means is that zero, the velocity zero, is within a thermal velocity of the wind velocity at that point, which means that every place in the star that has velocity zero is inside the resonance zone. So this includes the entire stellar interior. And of course, it's complete nonsense to assume that any of these variables are constant in the stellar interior. It's also not appropriate to use the Sobolev approximation in any regions that have high V curvature, so high change of the velocity gradient. Again, because this is also one of the macroscopic variables that needs to remain constant, and if there is a high V curvature, this is not constant. And this is the case, for example, at the sonic point. Okay, now another thing is that until now, it's quite nice, the results that we have, but they're maybe not very useful because all of this approximation was saying we only have one spectral line. A photon only interacts once inside the star because there's only one line. But of course, this is not true. So in order to make this more usable, people have made some extensions of Sobolev theory. So one important one, of course, is adding the continuum radiation, which has been done. The other is including higher terms of S, so gradients of S. So instead of saying, okay, source function is constant, you include terms that have some sort of source function gradient into the approximation. Then multiple line effects. So of course, if you have multiple spectral lines, the fact that there is this local Doppler-shift means that in the local frame, some spectral lines that were separated can be redshifted into each other and to overlap. And then lastly, there's the so-called method called Sobolev with exact integration, or SEI. And this is a combination of this formal integration, the explicit one, with the Sobolev approximation. So what is done is we don't compute the intensity itself across frequency with Sobolev, but only this this profile weighted mean intensity using the Sobolev approximation. Then this is used to feed into the rate equation, so compute population numbers of atoms. And from this, we actually obtain the source function. So the whole time we had the source function here, and we knew that it has something to do with how atoms treat radiation. But this is actually where it comes from. So the population numbers of the atoms make the source function. But then we, of course, see that the source function itself feeds back into all of these equations. So this requires some iteration, and this is an iteration that all of our stellar atmosphere codes do until it converges into a consistent solution. And then you have a source function that is calculated in the Sobolev approximation. And then you can use this source function to perform an exact integration in order to get the emergent profile, so the intensity as a function of frequency. So this is what these stellar atmosphere codes do. You first converge and converge and converge, and at the end, you perform the formal integration. Okay, now we'll take a small drink because this is a thematic break. All right, so we have the Sobolev approximation that we can use now to compute intensities to feed into radiative transfer. And now alternatively to this, we have to ask the question, what do we do when this doesn't work? And for this, we have the so-called comoving frame method. And I'm not going to go in so much detail with this one, as I did for the Sobolev approximation, but just outline the main steps. So we go way back to the radiative transfer equation and write it in a slightly different way, namely in the comoving frame. So we have the emissivities and opacities, and these are dependent on the local frequency as seen by the atom. So this is the frequency nu, but Doppler shifted into the local frame. So again, you have this comoving frequency, which is this Doppler shifted frequency. And then what you do again is some transformation of variables. So this d over dz will change, and then you have a component that is just purely a spatial component, but then of course also the change of the comoving frequency with respect to z. And what this means is that this radiative transfer equation, which is, by the way, an ordinary differential equation, changes into a partial differential equation. So you get this extra term here, this geometrical factor q, which also popped up before. And then this equation is then one that has to be solved numerically. By the way, I just want to say, this is valid for V is very much smaller than C. So this is a non-relativistic limit. Otherwise, you would have to include higher terms of V over C. Okay, so what we do with this is just integrated. So there are many different schemes to use this, but they generally divided into so-called implicit or semi-implicit schemes. And these schemes are stable, and they enable us to solve this equation and obtain, like all other methods, obtain the intensity as a function of frequency and space. What are the advantages of this? Well, firstly, we only have to actually consider a very small range of comoving frequencies for each line. Again, just the range around the line center, so not the entire spectrum. So this saves a lot of integration time. Secondly, a big advantage is that these emissivities and opacities are isotropic in the CMF, so you don't have to consider that the direction matters anymore. Third advantage is that J bar and H bar, which as a reminder are used to calculate the rate equations and the acceleration, don't need to be transformed into the observer's frame. So they can stay in the comoving frame. And issues that arise from this is that, like I said in the last slide, it only covers the non-relativistic limit. So for the relativistic limit, requires some extra terms. And boundary conditions are usually an issue, as it's a very common thing with partial differential equations that you need boundary conditions and initial conditions, and these need to be chosen very carefully so that the numerical errors from those conditions don't propagate through the entire solution. And then the question is, how does this actually compare to this Sobolev approximation? So the first thing is that one can show relatively easily that if you neglect this spatial component here, so the d over dz component, and you turn this back into an ordinary differential equation, you obtain the same solution as you would get with the Sobolev approximation. It's exactly equivalent. So what are some results from this? So this is the last part. So Sobolev is an approximation, whereas the comoving frame method is more exact. It doesn't really require approximations. So here we have this emergent line profile. It's calculated both by the Sobolev method and by the comoving frame method. So you have this typical P Cygni profile that we see. And you see you have the Sobolev solution, which is the line that has this sharp drop. And then you have solutions for different V Doppler over V infinity. And what this V Doppler is this velocity of the random motions of the particles. So this is not just the thermal velocity, but this includes turbulence. So it can be quite big if we have a lot of turbulence in the star. And here you see how it is for 10%, 20%, or 30% of the wind velocity, the terminal wind velocity. And what this shows is exactly, it mirrors the assumption that we made for the Sobolev approximation, that the smaller this Doppler velocity, the smaller the resonance zone, and the closer you get to having a valid approximation with Sobolev. Same thing we can see with the source function, the radiative acceleration. Another key aspect is here you see source function radiative acceleration as a function of radius in the star. So on the left, the parts that are very close to the surface, and on the right, the parts that are much more in the wind. And here you see again in the dashed line is the Sobolev approximation compared to the solid line, which is CMF. And you see that they match very, very well in the wind, which also, as I said, for the Sobolev approximation, but they mismatch in the interior part, again, because for lines below the sonic point, Sobolev approximation is no longer valid. And then there's one more thing, is that there's also this source function dip, which you see here in the comoving frame solution, which is not reproduced by the Sobolev approximation because the Sobolev approximation assumes a constant source function. So what this means is that in reality, the radiative acceleration is not well reproduced by the Sobolev approximation in exactly the sonic point, so close to the critical point. And this creates large errors in calculating wind driving, mass loss rates, and all of that stuff when you do hydro simulations. Okay, so after this, it's time to summarize a little bit what I've said. So I showed you two different kinds of theories of how to treat this radiative transfer in the expanding medium. One of them is the Sobolev theory, which is very fast and very elegant, and you can use it to calculate radiative transfer in wind lines. So anything that's above or well above the sonic point, and if the velocity gradient is constant. And for this, we use the concept of the so-called resonance zone, which is the zone where a photon interacts with the medium, considering a single line. And approximating this resonance zone as being very small meant that we could reduce the double integration essentially to just a single expression. So this is very, very powerful, and it's particularly powerful when including all of the extensions that make it more realistic, such as the continuum, multi-line, and especially this Sobolev with exact integration method. Okay, and then for everything else where you cannot use the Sobolev approximation, such as for these quasi-photospheric lines, then you have to use the comoving frame method. And on that note, I thank you all, and I welcome questions.
Thanks a lot, Joris, for this fantastic talk. It's not every day that we have the chance to go through equation in the so peacefully mode. I really, really appreciate your talk. Do we have questions in the audience? Please raise your hand or just unmute yourself or even write in the chat. No questions. What happens? Well,
I guess most of the people have to digest what they have heard. So,
exactly.
but that's real physics, particularly physics of radiative transfer. And it was a very nice talk in my perspective. And I guess everybody should have understood when one can use one of these methods, what's the advantages, disadvantages, and particularly what are the assumptions behind it. And this is important to finally to see which of the methods can be used. Sure.
Well, we have a few people saying thank you for a lovely review and nice talk, but still no question. So
I have a question, but so I admit I am new to this field. And so I would like to read more about this. Is it possible to somehow access the slides later on?
Yes, so the talk itself I think will be uploaded, but I can share the slides as well. So I was planning to do this. Yes.
yeah,
All
sure.
right.
Sure, Joris, you can send me the slide, and I can, if you want to share them, it's up to you, and I can send them when I send the link to the recorded talk.
Mhm.
Will this
Okay.
be posted somewhere in the internal University of Heidelberg system? I'm not part of the University of Heidelberg.
I will send an email to the Massive Star community as always through the
Okay.
emails. So if you receive my previous emails, you will receive mine also.
Right. All right. Thank you very much. Thank you. And thank you for the talk.
Okay. Do we have any more science questions related? No?
Maybe if there's no questions, I just encourage everyone who's in the same position as me to do a talk for the next semester, because I feel like I really learned a lot, and this is not the kind of topic I would have maybe looked at in so much depth. And Joe was also a very good supervisor and sent me a lot of resources, and we had a lot of very interesting discussions. So I feel like I learned a lot more than I had the time to share with all of you now. So yes, if you want to give a talk next semester, this would be great. So
Thanks a lot, because we need speakers. So thanks for the feedback. Okay, well then I think we will wrap up now and thank the speaker again and thank the supervisor too. And then we will meet in a couple of weeks now because we have Easter breaks and so other stuff. But we will meet in sometime in May for the next talk.
Joris, please remain online. And for the others, I also say thanks a lot for coming. And I hope you keep your interest. From next time on, we will apply all this, what we have learned today, namely to construct the line acceleration from this formalism, which we have just heard about by summing up now over different lines. And then we can get an not artificial, a analytic description in very easy terms of the total line acceleration, and then we have to plug it into the hydrodynamics, and then we see what comes out, namely a so-called line-driven wind. So this will be in short what we are doing next time. And then, of course, we will also speak about current advances in this respect, namely how we model these kinds of line-driven winds. So thanks a lot for coming, and see you hopefully on our next date.
And Mikhail, I think we can stop